Okay, are we ready? We're in the home stretch. So we'll finish this up and then move into atmospheric. Okay, so two-line atomic fluorescence. This is a technique that you can do relatively easily. You just have to seed your system with some appropriate atomic line source. So in this case, people have been using indium. It's a pretty common one. And what you want to do is choose your transition so that you can measure the population in two different lines. Okay, so electronic states for your atom, right? So in this case, there's the doublet P 1/2 is the lower state you want to know the population of, and the doublet P 3/2 is the upper state, so labeled 0 and 1 in that figure up on the upper left. So you do a transition up to an excited state, the 6 doublet S 1/2, and then you can measure the Stokes line from that transition. So you make that measurement. You can then tune and get your to a different transition between state 1 and state 2, let's just call it that, and then look at their anti-Stokes transition, and that will give you the population for these two. The intensities of the fluorescence there would give you the populations of state 0 and 1, and then use a Boltzmann distribution to understand, to try to get your temperature from that. So that measurement. So people have been using this pretty extensively. This is a typical setup. You do have to have a laser, but it's not a super fancy laser. And you make your measurement with, so these are two different laser lines, two different wavelengths. So that's why you have two different laser systems there. If you have a stable system, I think you could probably make the measurement with just one laser and you tune between the two different lines. And here's an example of the Stokes fluorescence, the anti-Stokes fluorescence, and then they backed out the temperature from the Boltzmann distribution. Okay, and then this is a comparison of this technique with the thermocouple. So it actually agrees pretty well with thermocouple measurements, depending on what your uncertainty that you're targeting is. Okay, so how well do you need to know your temperature? I'd like to see a review of all the types of temperature measurements and results for systems. It would be really nice to see that. Okay, so here's another TLAF type measurement. This was, I included this because they actually made the measurement in 2D in a different type of flame. So I just thought it was actually interesting. They also used indium and also made the same type of measurement. It's just a different group. And then they compared. In this case, they also compared to two different measurements, and I can't remember what the broadband and narrowband refer. Yeah, they use a narrowband laser and a broadband laser to try to compare to do these measurements. Yeah, and they compared that with the thermocouple measurement. Okay, so there are those results. Here's another technique called filtered Rayleigh scattering. I'm not sure, I haven't seen this technique used a lot in sooting flames, but this is a technique that's very frequently used in flames that don't have soot in them. But I'm going to show you some results that I just saw in literature for a sooting flame. So this is where you take a laser, send it into your flame, and you get Rayleigh scattering. And if you have if everything is sitting still, the scatter will be a pretty narrow line. But if you have your species that you're scattering from are moving, you're going to have a broadening of that line. And you usually filter out why it's called filtered Rayleigh scattering is you filter out the elastic scattering, so the exact same wavelength as your laser, and then you look at the line broadening to tell kind of, it's like the Doppler effect of the molecules are moving at you, molecules moving away from you, and you really want to understand, what that broadening, the Doppler broadening gives you a sense of the speed at which these things are going, and gives you a temperature. Oh, I have a soot meeting I'm missing. Okay, so that's filtered Rayleigh scattering. So, so here's a comparison, and I can't remember. So it's filtered Rayleigh scattering compared to something, but I can't remember what that is. And so here, so this is the only measurement I've seen with this technique in a sooting environment. So you can see they actually say here are the soot regions, so you get a sense of the measurement, but I think in the sooting region itself you might not have a good measurement. Okay, but it might give you some idea of the surrounding areas. But yeah, it's not a technique usually used for sooting flames. Okay. So this is a technique that actually people have used a lot for many decades to measure temperatures, gas phase temperatures in flames. It's laser-induced fluorescence, the same thing I was talking about with the atomic fluorescence. In this case, you're not doing different electronic states, you're actually looking at internal rotational vibrational states of usually a diatomic. In this case, it's NO or OH are the two common species that people use because they're very easy. You have a pretty good laser-induced fluorescence transition that you can access pretty easily. So people use this technique, have been using this technique a lot, and you see they have, they're measuring all these different lines for different transitions and use a Boltzmann equation, Boltzmann distribution to back out the temperature. Here's another one. I think the left one is OH and the right one is NO. And here's what they get. So, so the Boltzmann equation is, and you basically use that equation right there that I have PJ is equal to 1 over Q times E to the energy difference between the initial state to the next state over the KT, and T is temperature. K is a Boltzmann constant. So now if you plot that on a log plot, it should be a straight line, and then you can fit it and get a temperature out. There are some drawbacks a little bit to this tech. Here, let me go back. There are some drawbacks to this technique, and I don't know how much of an effect it makes, but you can, depending on if you do this on the nanosecond time scale, people have pointed out that you can get quenching between of these excited states that are gas dependent, so you don't actually measure the fluorescence. You end up getting quenching with collisions with other gas phase species. If you do this on a shorter time scale, it's actually more accurate. Okay, or what the quenching factors are, and you can factor that into your calculation of temperature. Okay, so another technique that's really nice is CARS, coherent anti-Stokes-Raman spectroscopy, and this has been used for decades, and it's been implemented in a whole bunch of different ways. The most, sophisticated approaches use really fast laser systems, and where you can get these basically phase matching type of conditions where you actually don't need to have a whole bunch of beams coming in and going out, which is a standard way. So let me see if I put this. Okay, yeah. So here's kind of, this is from Sean Kearney's group at Sandia in New Mexico, where they use a femtosecond laser system and cross the beams. And so you have a pump beam, a Stokes beam, so you stimulate that, a probe beam, so that's another color beam, and then you get the CARS signal is what you measure. right, with your detector. You disperse that and get a spectrum, and then you can use that distribution. So it's kind of like doing LIF, but doing it all in one at one pulse, right? So you can basically get a temperature in a single pulse. So instead of tuning your laser to try to pick out all the lines, you can use this technique to get your lines in. So if you have a turbulent flame, for instance, you could get instantaneous temperature. You can actually so here's an example of the results. So the left side is a shot average, and the right side is for single shot. And you see, you actually get really good spectra even for single shot with this technique. If you set it up, I've never done cars, actually. I always am like amazed by people who do cars, because they look at their laser systems look so fancy. But I don't think it's that hard. I think, there's some complications with the analysis, but if you just talk to someone who does cars, there's usually a cars code that they can give you to help you do the analysis of the signal. Okay, so let's see. Here's a comparison with other measurements. So you can do this with a nanosecond system, but you can't easily do this measurement with a nanosecond system if you have soot, because on a nanosecond time scale, you actually have the complication of laser-induced incandescence from your soot particles themselves. So you have this really broad background that can make your signal really hard to see or hard to interpret. So normally when people are doing this for a sooting system, they use these femtosecond or picosecond type setups that allow you to actually do the measurement with a much shorter time scale in a pulse regime where you don't actually get LAI. Because remember, I was saying that you can't do LAI with a femtosecond laser because the excitation, you don't have a fast enough distribution of the energy into the thermal states of the molecule, of the particle. Okay, so you can see that, yes.
Could I make a quick announcement?
Yeah.
Sorry, okay.
Yeah.
As you can see, the university is undergoing a lot of constructions, okay? So Tuesday, I'm gonna let you have the email. No, can you hear me? Okay. Email tonight, I'll tell you. Tomorrow, the whole building will be chilled for some reason. I don't know what. They say it'll be very cold. Dress up warmly. Okay? Tomorrow. Friday, a little bit even more complicated. We are moving to another building. Okay? Friends Center, that's where we usually hold our meetings. Friends Center on Olden Street. You can look at the map. Okay? It's around the corner from the Tiger Inn. But anyway, tonight I'll let you guys know. So it'll go to there for Friday. I cannot protest. I cannot do that. The university wanted to do it. I just heard of it just then. Okay? All right. So that's
All right.
really it. Okay. Back to you.
All right. Thank you.
Great.
Yeah. Okay. Okay. So these techniques seem to work really well when you do the comparison. Okay. And here's an example of, where they actually did the whole measurement with a laser sheet, so they actually could get a line temperature, like they actually could get spectra at a whole bunch of different heights in the flame simultaneously. So these techniques, people who are developing them are very clever and are figuring out ways to implement these, and ways that make it so much easier to get temperature distributions of like spatially all at one time. And let's see, this was in a sooting flame, in fact. So they used nitrogen, oxygen. They saw hydrogen. In fact, they could even get the populations, the densities or concentrations of these small species while they're making the temperature measurement in a sooting flame. Yeah. Okay. So here's another example where they're doing 2D femtosecond rotational curves. This is using N2 as the gas. And you see that they actually, this is where they can use, they can actually get a distribution of temperatures spatially all at once. These are all individual, so each of those panels up there is an individual state that they were probing. And they could see, like, get Carr's signal all the way up to the wall inside they were doing some shock experiments. They were doing that. Okay. Yeah, there's a lot on Carr's because I think it's a really, really great technique. And you know, one thing you can do too is collaborate with someone who has the technology to do this. And usually people are very, you know, they have these big lasers. Usually they're very willing to collaborate. So if you're looking for someone who might want to collaborate, let me know. And not that I can do it, but I know other people who might be willing to collaborate, okay? So here's another situation where they're using Carr's in a flame. I won't go into, I was just excited when I was like finding all these papers, like, oh, this is a cool one, and this is a cool one. This one actually shows that you can get gas composition. So you can do Carr's for N2, H2, and CO in the flame. So you can see they have different spectral features for the different small species. And this one actually is LAF. So here's where you want to get, if you want to have information about the composition inside your flame, the gas phase composition, it's nice to know what the radicals are. OH is a big one, especially if you're studying oxidation, right? Oxidation goes quickly with OH. So if you want to, oxidation of subparticles goes very quickly with OH. It's a big, you know, oxidizer. So you might want to have lift measurements of OH in your flame. So again, you can like use this technique to measure OH. You can measure NO. There are a whole bunch of species you can measure using LIF. Okay. So here's another one. This is PAH LIF, right? So PAH LIF is a lot harder than measuring these smaller species like NO or OH. Because the molecules are large, right? And they're actually very similar to each other in electronic structure. So as they get bigger, you're going to have a red shift for your spectroscopy, for your absorption and emission. But mostly there are these broad features. And then if they're hot, they're even broader. So you can kind of get an estimate of size, like, you know, how big, you know, these people were like trying to like measure LIF of different species, right, in a flame. But it's hard to actually nail that down when you have a big broad feature, like, you know, say the outer curve, that big black curve is the feature you see, and then you're trying to fit it with all these other smaller curves that, you know, that you have to measure the temperature of those, temperature dependent spectra of those, and then try to back that out and fit it to the big curve. So there's a lot of uncertainty in trying to get PAH from LIF. It's not, you know, it can give you kind of an idea of where you have pHs, but I think it's beyond that, it's a little bit hard to do. Okay, so then this is a nice, interesting experiment where instead of actually trying to get the PAHs in situ in the flame, they actually extracted from the flame and did an online measurements. They cooled, so they extracted from the flame, cooled the gas phase species, and then did the spectroscopy on them. So you can actually say, okay, I have pyrene. I have, you know, you get the real spectrum of the species. So so they've been extracting and cooling in a molecular beam and doing these measurements. And you see what they're seeing is, you know, that's what pyrene looks like, you know, at the top. And then pyrene at different concentrations, and then compared with the pyrene extracted, the species extracted from the flame, it looks a lot like pyrene. Okay, it's really nice work, and when they plot it out, it is really consistent with what people get with mass spectrometry. And this is an example. There's C-pyrene for a premix flame. It's actually kind of interesting, and I don't understand it, but a species like pyrene will actually increase. You kind of expect that as a function of height above the burner. It will increase. Then it goes through a little dip, and then it increases all the way up. In a diffusion flame, you'll get, it'll increase and then just decrease as it oxidizes away. I don't know why it dips and then goes up again, but that's a pretty common result. Okay, and then we go to another online technique is molecular beam mass spectrometry. So I've been talking to you mostly about aerosol mass spectrometry, where we suck the particle, everything out of the flame. We make a beam of the particles. They hit a plate, we heat them up, and then we vaporize them. This, you just extract the gas phase right into your mass spectrometer, ionize them, and then get the mass spectrum. And then you can ionize in different ways. In this case, I think they were using a synchrotron maybe. And this is Katarina's group. And they get really nice mass spectra of all these different species. And then they can do, if it's at the synchrotron, then they can tune the photon energy. Another thing they can do for this type of experiment is, instead of using a synchrotron, if you use resonance-enhanced multiphoton ionization, it's kind of very similar to doing a LIF experiment, except instead of getting fluorescence after you excite the molecule with your laser, you ionize the species with the laser. And then you can selectively ionize a particular species and get the see if you see the species in the mass spectrum. So people will do that if they're like, oh, is that, mass 152, is that what I think it is? They'll try to come up with a REMPE scheme to do that, to ionize it and see if they see it there. Yeah. Okay. Yeah, so here's the comparison of the gas phase with the VUV AMS, so you can see the differences between the type of data I was showing you, which is the lower right-hand panel, that's with the aerosol mass spec. The same flame at the top using the molecular beam mass spec technique shows you a very different spectrum, because it's showing what's in the gas phase versus what's in the particle phase. So you tend to see a smaller species. Yeah. Then you can do GCMS to get composition, gas phase composition. This is also a great technique because it helps you get the isomers at a particular mass, because you have you suck from your sample, right, into a gas chromatograph with a carrier gas. So this is like a heated, column, and different species with different structures will spend different amounts of time in the column because they'll be attracted to the column walls like differently. It's kind of a gas surface type of interaction. Not that you can actually predict, but you can put in references to see what those retention times are for different species. And then once you get that, then you can get the mass, and you can couple the mass spectrum with the gas chromatography. So you can get, so if you have one particular mass, like say you have mass 202, pyrene will have a different retention time from fluoranthene, and you can say, oh, it's pyrene or it's fluoranthene when I see that mass 202. Yeah. So this is actually a really nice technique, and it's relatively straightforward. The only disadvantage I see is that you can't see radicals very easily. And then you also have to extract from the flame if you're worried about extracting. That introduces the same probe problems we've been talking about. So here's another example. We have online gas chromatography with mass spec, GCMS. In this case, they actually said, okay, as a function of height in the burner, we see both, at the bottom right, we see both pyrene and fluoranthene. So that's another measurement, and that's determined through gas chromatography with mass spectrometry. Yeah. It gets overwhelming when you look in the literature at how much beautiful work people have done. You know, it's kind of cool to try to put it together. Yeah, so here's another example of, you know, with GCMS, you see the different isomers. Okay, so this is what we've done. We've now gone also, we filled in all these different techniques for particles, and now we've done a little bit for composition and for temperature. Okay, so now I'm going to switch to, should have had this queued up. Just have to find this now. Okay. Okay, we just started day 3. Right. Okay, so we're a little behind. Okay, so yeah, so here's, let's talk about atmosphere. Okay, and here we're going to talk about atmospheric emissions, atmospheric processing and aging of soot particles, measurements, and climate change. So we'll touch on these really briefly. We don't have a lot of time, so I'm going to try to move through the material kind of quickly. So remember, we've been talking all about the particles. Like, we did a little bit of coding and restructuring. This is really important for the atmosphere. Particles will be coded in the atmosphere, and this is something people worry about all the time in atmospheric science, is, you know, what's happened when the particles age in the atmosphere? How does that affect all their properties? It's also important for health effects. Okay, so I'm going to switch over to how atmospheric scientists talk about soot, right? So they don't actually usually call it soot. They usually call it black carbon. And they say black carbon is the stuff that comes out of combustion, right? So, you know, but it's also other things that are black, and it's not clear that what that actually entails. So they have all these different ways of classifying it, and it's based on their measurement techniques. So, so I've added on the right-hand side our terminology for these different types of particles. So they'll talk about organic carbon. When we talk about incipient soot, they'll talk about organic carbon, or OC. And then they talk about refractory organic carbon, and then elemental carbon. So elemental carbon is our what we call very mature soot. So when they make a measurement, they'll make a measurement and say, okay, we have this much like elemental composition of H and C and whatever. We call that organic carbon, and then all the real almost pure carbon is elemental carbon. On the right-hand side, so that's organic carbon. So notice that they say it's colorless and non-refractory. Exactly what we say, right? And then I've added the word brown carbon in the middle. They often call the colored organic carbon brown carbon, okay? We would call that like soot that's not very mature, or young soot, because as soot goes from incipient, it goes through a range, you know, between incipient and mature. It goes through a range to where it's kind of brownish in color, and I'm sure you've probably seen this on when you're, you know, like doing a barbecue, right? That sticky stuff, that's a lot like what the brown carbon is. It's not that puffy black stuff that you get coming out of the flame. but that sticky stuff, and it's really hard to get off your fingers and stuff, that's our brown carbon. And then the molecular structure, look at they have similar type of description of the molecular structure. We have graphene layers, turbostratic, graphite, graphitic. They talk about humic substances. That's related to biological materials that are kind of not fully graphitic, fully carbonaceous. And then we have low molecular mass hydrocarbons and stuff that we think about. Most of the black carbon and brown carbon come from anthropogenic sources. So if we're worried about these species in the atmosphere, to this point, a lot of them come from anthropogenic sources, though we are actually starting to get more and more non-anthropogenically generated particles through wildfires, where we're not directly involved. Though a large fraction of wildfires are started by people. In fact, I think I might have a figure, we'll come to it. But what's outlined in black, I don't know if you can see that, that starts from on-road diesel and then wraps all around to deforestation, that's included as anthropogenic sources. The part that's not considered anthropogenic is wildfires or peat bog fires, so woodland fires are considered, anything that's out in the wildland, we can call a wildland fire. Wildfires I kind of think of as uncontrolled fires. Okay, so most of this is anthropogenic. A lot of it's from heating and cooking. Okay, so and a lot of it comes from developing countries, where a lot of their heat is from solid biomass. Okay, and as we were talking about before, these emissions actually look very similar. The characteristics of all these particles, it doesn't seem to matter where they're coming from. What's interesting, and we haven't talked about yet, is from a wildland fire, from a wildfire, you get something that's called tar balls. I think this is really fascinating. This is organic material that condenses in these large, like organic spheres. And there's an example of one right up there. I think that might be kind of like our incipient particles that are coalescing, combined with emissions, like, we have these species that can't condense in the flame, but once they get out of the flame, they can condense. And I think that, our incipient particles are collecting along with some of these other species, making these big tar balls. So they're not graphitic, they're amorphous or goopy things. There's a lot of concern about them because people think they actually have a significant climate effect. They absorb pretty strongly. Okay, so so when we're talking about this type of process, we have to think about how we're actually generating our particles, right? When a lot of these species are generated from biomass, right? So we go through a process where, here's our biomass, it's a match, right? I just got from the web. And as the match heats up, so this is one of the reasons why soot is important in propagation of fires, is it radiates heat. So it can radiate to the biomass surrounding the particular flame, right? And once you start to heat up this biomass, it's going to emit these hydrocarbons. This is going to be the beginning of our fuel, right? So we normally think of our flames. When we have what we call flaming combustion. So when we actually have a flame, we're going to be burning gas-phase species. So you basically start with, when I talk about pyrolysis, I usually think in the chemist version of what is pyrolysis. it is like the breaking apart, or the high temperature chemistry is technically, in chemistry, is what pyrolysis is. In this case, people think of pyrolysis as the emission of a lot of these volatile species or semi-volatile species from heating up the biomass or the wood or whatever, the peat, what you're trying to get these species. Just like what happens in a regular flame, you have, these things get ignited, the species crack, you have radical species, and then you get our gas-phase species. Notice how the temperatures are very consistent with the temperatures we see with soot formation. So we're starting to actually see things that we're familiar with. Once we get that volatiles out of the biomass, then we can understand what's going on, right? We study this in combustion. Okay. So here's an example of how people think about the process. So you have heat, you generate these species. The species that we often don't think about this part of it either is the species that get to the point where they're not combusting anymore and there's no more chemistry going on. Those become char. Char is the part that's not burning. Okay, so you end up usually leaving char behind when you have a wildfire. Okay, so, and those are the combustion emissions. At the top, you end up with gases, these tar or tar balls, like the stuff that goops up, and soot, okay? And then just like in a flame, we start, like what we call a smoking flame is when we're doing experiments in the lab. A non-smoking flame is the type of flame where you have a tip to your flame and the soot particles are oxidized as they go out the tip of the flame. A smoking flame is when you're flowing too fast for that to happen, your fuel too fast for that to happen, and you don't have full oxidation of the soot as it goes out the top of the flame. That's called a smoking flame, so you'll have soot emissions. So when I usually use non-smoking flames when I'm doing these experiments, but you can, people also do smoking flame experiments, and often in a forest fire, you're gonna have a smoking flame. Sometimes you're gonna have, the flame will be quenched, you're gonna have turbulence, you're gonna have winds, you're gonna have a lot of different factors that complicate everything. Okay, so now you have your combustion emissions and they go downwind. Okay, so here's kind of like how people think about forest fires. So there are two regimes that people normally think about. They think about flaming fires. Those are what we're familiar, what we've been talking about, right? Those are the ones where you have a flame front, it's hot, it could be, usually it's, in this case, it's diffusion controlled because your air is coming into your flame from the outside. Or you can have smoldering. Smoldering is when you have oxidation of a surface. So you often don't have the flame, you just have oxidation of the surface that still generates particles, it still generates pollutants. In fact, it generates like a huge amount of particles and pollutants. That's called a smoldering flame. And you don't get mature soot from a smoldering flame. So when people are trying to analyze what's coming out of a forest fire, they're trying to figure out, how much, what part is, is it flaming? Is it smoldering? Like, where are we in these regimes? And how is this process occurring? Okay, so on the left-hand side, a peat fire is usually a smoldering flame. And you've probably heard about these peat fires where some of the, these peat bogs or this peat can be, like the fire can be underground and can be a smoldering a fire for like decades. Like it can underground and then just keep emitting all these pollutants. And it's really hard to put these things out, but they pollute a lot. And then there's the flaming fire. But in this case, if you have the residual like this, you're starting to go out, it can turn into a smoldering fire. right? So you kind of like probably have seen this, your campfire is like still kind of smoldering and emitting smoke, even though you're not seeing big flames coming out. Okay, and then firebrands are interesting. Those are a way for fire to propagate, and this is something that's not really understood all that well. So it's pieces of flaming material that are emitted from the fire and then travel, and then they can land someplace and like start the ignition. Okay, so this is something that people worry about, and in fact, when you're talking about these urban, like wildland, these fires, okay, there's a term people are using all the time these days. It's called WUI, W-U-U-I. It's called wildland urban interface. So these WUI fires are becoming a real concern. This is where you have your wild, your mountains. So this happens in Colorado, right? You have your mountains, your woods, and then right next to that you have your city. So this happens like in Boulder, right? We worry about this a lot. You have a wildfire that starts, in the wildland part or in the city somewhere, but you have this competition or complication that you have all this dry wildland, and you have this fire spreads right through a city. And this has been happening over and over again now lately, where you wipe out an entire city, and then people are worried about the structures in the city. But in Boulder, we actually think, especially the houses that are more on the edge and like going up into the mountains, they try to construct these buildings now. The new construction is, they try to make the doors so they don't blow out. The windows are because once you get air into the inside of the structure, it can just ignite the entire inside. So they're trying to make these really airtight. So if there is a wildfire, you're not going to have this like big, you're not going to destroy your entire house. So they're trying to make it out of fireproof materials on the outside, seal the entire house. But the problem is these firebrands can actually sneak in through cracks in the buildings. They can actually go in through, like, the underneath the roof. And so now people are trying really hard to figure out where you could get firebrand sneaking into the house and then igniting on the inside. Okay, so how are these fires started? Noticed that 4th of July is a peak in fires ignition, and notice how many of these fires are ignited by people. People having barbecue, or mostly people having a campfire. There was one, you probably heard about this, it was a gender reveal party where they, had some kind of like firework in a bad area in Southern California, and it caused huge fire. So we are responsible for a lot of these fires, and you see these fireworks just like are a real serious problem in some of these areas. So here's wildfire trends, right? So this is in the western US. As a function of year, the frequency of wildfires is increasing dramatically, and the size of the fires are increasing dramatically. And this is largely because of climate change, as everything gets dried out. Here is kind of a map of trends for different regions. Some regions aren't seeing more wildfires. Some regions are seeing more. I know so Rocky Mountains is where I tend to think about, and we definitely are seeing more fires, and they're bigger. And it was just a year and a half ago that we had a big fire that wiped out 1,000 homes right outside of Boulder. Okay. So what do the emissions look like? So this is what emissions look like from a smoldering fire, right? So this is, so I was talking about tar balls. This is that, I just find this it's just really fascinating. So from a smoldering fire, you're not going through a flame front, right? So if you're not going through a flame front, we've been talking about this for the last 2 days. If you're not going through a flame front, you're not getting mature, right? You need that high temperature to help you get rid of the hydrogens. A smoldering fire does not do that. So you end up with these like less mature particles. They're going to coalesce. They're going to accumulate other hydrocarbon species. They're going to grow, and it's just and people are starting to really focus on these things, these tar balls. So here's what then, if you have a flaming fire, like it looks like what we're familiar with, right? All of us working with flames, you see this structure, this, like aggregate size. What's different between studying diesel emissions or engine emissions, like aircraft emissions, diesel, gasoline is a little bit different, but these types of particles from these engines tend to be much, much smaller. So they tend to be on the order of 100 or so nanometers. Particles from forest fires can be huge, largely because you're getting a lot of these particles and they're clumping together, and that's why you see them. Like, when we see a diesel truck now, you don't usually see a lot of coming out of the stacks. Where you used to see all this black stuff, engine technologies have improved in the last couple decades. So you don't see so much of the black stuff, but when you have a forest fire, you're gonna see a lot of this black stuff, and its concentration is high, so we get what's called a super aggregate. People can generate those in the lab. It's usually when you have high concentration of particles, and those particles agglomerate. So remember, aggregates bound tightly together, agglomerates like not tightly bound together, and they can fall apart. Yeah. So remember, dispersion exponent, call it the angstrom exponent for atmospheric sciences, right? Look at this. Look at this. This is a paper about biomass burning aerosols, and they're measuring the dispersion exponent. They're trying to figure out, so when they see a high dispersion exponent, what do you think they are attributing that to? Okay, I'll give you a multiple choice. Is it smoldering or is it flaming? Hannah? Smoldering, right, is smoldering, right? So because you're not getting mature soot, right? So and if it's not mature, high dispersion coefficient, right? High dispersion exponent, or angstrom exponent as they call it, in atmospheric. Okay, so this is another study where they're trying to map out the dispersion exponent and try to understand what happens to the particle as it's evolving in time and space, as it's being transported. So they actually use it as a tracer for biomass emissions. They're like, okay, I see this, I see these particles, they have this dispersion exponent, they must be coming from a smoldering flame, so fire, so we're gonna see if we can understand what else is emitted in these smoldering fires. Yeah. Okay. Yes, okay, so here's the experiment I was talking about. When in the field, atmospheric scientists see that there's an enhancement in the absorption cross-section when they have coated particles. Is this a science paper? Yes, this was reported in Science in 2012. Since that paper, people have been obsessed with this in atmospheric science. This is the paper that indicated that, so you see E absorption, and let's see, so non-refractory portion of particles, so as you increase the non-refractory, so you increase the coating on your particle, it looks like the absorption cross-section increases, right? We don't see that in the lab. My measurements haven't shown that, and everyone else who's measured in the lab hasn't shown that. So there's a real gap in our understanding. This is something that we have to figure out. And I think, the soot community is the community that should figure this out. That's what I think. But yeah, so, that's all of us. We're gonna figure it out. And if you figure it out, tell me. I'll be so excited. I'll recommend me to review a paper. Okay. Okay. So yeah. So here's, let's see, measurements also showing an increase in the in field measurements, right? Increase in that enhancement. And I think we're at the end. Okay, that's also about the enhancements. Let me just quickly go through. Okay, here's something else you all have to help with. People who do atmospheric lab measurements, the first thing they were doing was using premix burners. And I was like, no, don't use premix, because when you're doing atmospheric, natural flames are all gonna be diffusion. You have to use a diffusion flame. So they're like, oh, okay, we can't use premix. So they used the premix, they based all the results on premix flames. So, okay, what did they do? They started using this inverted burner. So now you see almost every atmospheric paper that comes out now is using this inverted burner. So has anyone ever used an inverted burner? On flames? No. Okay, you know what this inverted burner does? Okay, so the reason they use it is it's pretty stable, right? It's inverted, so you have buoyancy is matched with flow, right? You get long residence times of these particles in the flame. What that does is it makes the particles really mature because they're sitting at high temperature for a long time, and they get huge. This is not a natural flame. In that, a wildfire is not inverted. It's going to be like emitting. So tell your atmospheric friends, stop using these inverted burners and start and use a regular diffusion flame, and so that you get the right time scales for soot formation. Okay. Yeah, so I'm gonna skip over this because we're really at our time. I just want to say, okay, we can't do processing and aging. I don't have time, but I want to say, just look at your notes and say thank you. It's been a pleasure interacting with you and meeting you. I've had so much fun, and go and keep in touch with each other. Okay. Meet each other, keep in touch with each other. You're a great group. You're gonna go places. So do it, be brave, take risks, and if you ever have questions, call me, okay? Thank you. Yeah.